Alrighty, here are the solutions for the Chapter 3 homework. We're going to start with problem number 1. Big surprise. Problem number 1 is a 150-meter tall cliff. That's pretty darn tall. And we're going to throw a stone at 8 meters per second off of this cliff. This is clearly a classic problem number 1, a horizontally launched projectile. And it's going to land over here. And because it's classic number 1, we don't need to componentize the initial velocity, but we should probably specify that our coordinate system starts on the stone and has positive to the right, and I'm going to choose positive downwards. All right, so the list of knowns and unknowns. Now we'll put that right underneath here. Actually, why not to the side? Hey, what a novel concept. X and Y represent the final positions, the initial position being 0. And we don't know what the final position is horizontally. It'll be away from the cliff somewhere. But we do know the final position vertically will be 150 meters below the starting point. And since below is positive, that's a positive 150. The initial velocity in the x direction is 8 meters per second because the initial velocity is entirely in the x direction. The initial velocity in the y direction is 0 because the initial velocity is entirely in the x direction. Vfx, by dint of our cleverness, is going to be the same. That's because the acceleration in the x direction is 0. This velocity never changes throughout the problem. Vfy is going to be some large number we don't know. And the acceleration in the y direction comes from gravity, so 9.8 meters per second squared. It's going to be a positive because gravity pulls downwards, and I've chosen downwards to be positive. The time for the problem we don't know. So the usual approach to fashion will help us out. Part A asks us how long the stone is in the air, and for that I would use the y Swiss Army equation. There's the y Swiss Army equation. Now we're going to put in our numbers. 150 is the y, VIY is 0, and that's going to multiply t. That term is going to disappear and become 0. But then we have 1/2 of 9.8 times t squared. Didn't put a number in for t because we don't know what t is, so we leave it as the variable. There's a little arithmetic we can do right here. 150 equals half of 9.8 is 4.9 t squared. So that means that 150 over 4.9 is equal to t squared, and the square root of 150 over 4.9 equals t. And I'm going to get a calculator out here just as soon as I figure out where it is on this thing. Okay, 150 divided by 4.9 equals, and then I'm going to take a square root, 5.53. And that's the answer to part A. That's a longish time, but this is a very tall cliff. I don't know where you find 150-meter tall cliffs. Grand Canyon. Okay, next up, we're going to do part B, which is how far from the edge of the cliff does it land. And for that, I would probably use the X Swiss Army equation. Now, the X Swiss Army equation is really nice here because this entire second term is going to disappear and become 0. But let's see it happen. We don't know what x is, so we leave it as x. Vix is 8, and t is now known to us to be 5.53. On this next term, we have 1/2 of 0 times 5.53 squared. And that's why this term becomes 0, because we're multiplying by a 0 in the middle of it. So all we really need is 8 times 5.53. And that's 44.2, 44.3. Let's just keep 44. And there's B, 44 meters from the edge of the cliff. What is the vector velocity of the stone when it hits? Wow, that is going to be a little challenging because first we have to find the unknown y velocity, and then we have to combine these two in the x and y directions to find the final vector velocity. So let's quickly find the unknown final y velocity. I'm going to use the definition of acceleration equation for the y direction, and that's going to be 0 plus 9.8 times 5.53. Okay, so clear this out. 9.8 times 5.53 equals 54.2. So we have a vector that is 8, comma 54. Let's drop off the 0.2. And we need to convert it into an r and theta type of vector. That uses, what does that use? That uses Pythagorean theorem. So r is going to be the square root of 8 squared plus 54 squared. And that's going to be, well, I happen to have the 54 right here, so let's just square it, plus 8 squared equals, and now we take a square root, and we get 54.7, 54.8. That rounds up to 55. And that's one part of it. This is V final. R represents the magnitude of the vector. The vector we're looking for is the final vector. And then theta, I better circle this. Theta is equal to the inverse tangent. Now we need the opposite side over the adjacent side. And for that, I think a little sketch would be in order. We're going to have 8 meters per second of horizontal velocity, and we're going to have a gigantic 54 meters per second of vertical velocity. And so our vector velocity is this direction. And I want this angle right in here, the angle below the horizon. So I think the opposite side is the 54. 54, 8, and now let's get that going. Inverse tangent. Okay, I did something wrong. Shift tangent. Oh, I see. I have to do the math first on this calculator. 54 divided by 8 equals, and then we do inverse tangent on it. 81.6, so let's just call it 82 degrees. So my vector velocity when I hit the ground is 55 meters per second at 82 degrees below the horizon. Very nearly vertical. Okay, that's number one. I hope you got those answers. It's a classic number one problem. Let's look at number two. Number two is a little different. This is Janet, who is going to be, coming off of a diving platform into the water. And she's just going to run. And she's going to run at 2.8 meters. Okay, that's not running. That's a trot. 2.8 meters per second. We don't know how tall the platform is. Turns out it's going to be a pretty tall platform. But we do know that she's going to go into the water down here, and that the time is going to be 2.6 seconds. Well, that's kind of cool because the time is usually our first step. It seems like our first step is done for us. Coordinate system is going to be origin up here at the top, positive to the right, positive down. These are good choices for a classic number one problem. And now let's make the list of knowns and unknowns. Do we know where she's going to be? No, we don't, in the horizontal direction. And do we know where she's going to be in the vertical direction? No. Do we know her initial x velocity? Yes, 8 meters per second. Do we know her initial velocity in y? Yes, 0 meters per second. Her final velocity in x is also 8 meters per second. Her final velocity in y is not known to us. The acceleration in x is 0. Acceleration in y is 9.8. And the time is 2.6 seconds. So the big difference here is we don't know the distance she's going to fall in y, but we do know the time. And now we can answer part A and B in any order we'd like. Part A, how high is the platform? I'm going to use the y Swiss Army equation for this one. You've got to use a y equation to find a y altitude, y height. There's just no getting around that. Let's see, y is what we don't know. VIY is 0, meaning that entire term is 0, plus 1/2 of 9.8 times 2.6 squared. Don't forget to square. Many students drop the square at some point and get an incorrect answer. I don't want you to get an incorrect answer. All right, that looks like 1/2 times 9.8 times 2.6 squared, which is 0.5 times 9.8 times 2.6 squared equals 33.1. We'll keep the extra digit, 33.1 meters. That's 3 times as high as any Olympic diving platform. Then part B asks us to find how far from the base of the platform she lands. Well, that's a question of X. By the way, the base of the platform, I've drawn the base going in like this, so we're actually measuring below this point, below the point she launched at. So I shouldn't have drawn it with this relief like that, but that's something they do on real diving platforms to make sure that the diver is into the meat of the pool and not near the edge. Okay, so let's use the X Swiss Army. If you become an advanced life form, you can stop putting this term on the X equation because it constantly goes to 0. But hey, one time it saved me to do that. All right, so X is equal to 8. Nope, 2.8. 2.8 times 2.6 plus 0. All right, 2.8. I was trying to use the velocity from the last problem. 7.28. And that's problem number 2. Hooray! Let's do problem number 3. Problem number 3. An arrow is shot at a 30-degree angle and a velocity of 49 meters per second. We want the components. We want the how long it's in the air. We're just going to solve this like a normal classic number 2. All right then, the components. See, the original velocity is given to us as 49 meters per second, 30 degrees above the horizon. And we need to find Vix, which is going to be the original velocity times the cosine of the angle. In this case, 49 times the cosine of 30. That's going to wind up being 49 times cosine of 30 is 42.4 meters per second. We also need to know the initial velocity in the y direction, which is going to be VI times the sine of the angle. This is always true, at least if you measure away from the ground. It's going to be 49 times the sine of 30. Now I seem to recall that the sine of 30 is a half, so that's going to be half of 49, but let's just go ahead and do it in the calculator here. Yeah, 24.5. Okay, now that we have those two numbers, they go in the list of knowns and unknowns. Oh, coordinate system. Here, with up going positive and to the right going positive. That means that things are going to change. This is the opposite than we did with classic number 1. Final position in X we don't know. It's over here. Final position in Y is 0. It gets back to the ground. Our initial velocity in X is the 42.4 that we found. And initial velocity in Y is the 24.5 that we found. The final velocity in X will be the same number, 42.4. The final velocity in Y, we can pretend we don't know. It turns out that this will be the negative of that. We can prove that sometime. Acceleration in the X direction is 0. Acceleration in the Y direction, in this case, is negative 9.8 meters per second squared. Still gravity, so still 9.8 meters per second squared, but now downwards is in the negative direction. And the time, we don't know. Our normal first thing we solve for is what they're asking for first. Oh no, this is A, the components of the velocity. B, how long is it in the air? And for that, I like to use the Y Swiss Army equation. Zero equals 24.5 times t plus 1/2 of negative 9.8 times t squared. And as we talked about in class, this looks like it's going to be a quadratic, but we are allowed to divide through by t. 0 divided by t is 0. 24.5 times t divided by t is just 24.5. And this is 1/2 of a negative 9.8, so negative 4.9. And then times just t, not t squared, because we divided by a t. This negative term should probably come to the other side here. 4.9t equals 24.5. And now we'll divide 24.5 by 4.9 to get our time of flight. 24.5 divided by 4.9 equals 0.2. That can't be right. That doesn't look right. 24.5 divided by 4.9. Much better. That's dead even 5, isn't it? Wow, that is really cool. And now for part C. Part C says what horizontal distance will it travel? And for that we'll use the x Swiss Army equation. X equals 42.4 times 5 plus 0. X equals 212 meters. A couple of football fields. Dead solid, normal, classic number 2. Now, this one's the big kahuna. And we talked about this a couple times in class. So we have basically a projectile launched at an unknown velocity, but a 45-degree angle, and it's gonna go over here, and it's gonna land 98 meters away, or cross over a fence actually. And so when we componentize, we don't get an answer, we get a variable, VI cos theta. This pen is making me sad, which is equal to VI times the cosine of 45 degrees, which happens to be 0.707, so 0.707 VI. Similarly for Y, we get the same result, 0.707 VI. Even though Y uses the sine of theta, the sine of 45 degrees is exactly the same as the cosine of 45 degrees. Let me get rid of this black pen, it's making me unhappy. All right, my final position is 99.8. Oh my, that's a Freudian slip. 98 in X. My final position in Y is 0. My initial velocity in X is 0.707 of the initial velocity, and my initial velocity in Y is 0.707 of the initial velocity. Final velocity in X is the same as the initial velocity in X. Final velocity in Y, we don't know. Acceleration in X is 0. Acceleration in Y is negative 9.8, and the time is, I don't know. Okay, in this case, this is one of the rare times that solving the X equation gets you somewhere first. All right, and so let's do that first. To solve the X equation, we write the X Swiss Army and 98 equals 0.707 VI times t plus 0. So it looks like if I divide over here, I have 98 over 0.707 VI equaling t. We could also combine these two numbers. 98 divided by 0.707 equals 138.6. So we have 138.6 over VI equals t. But we can't go any further because we have two unknowns. So now we get going on the Y equation. Now I'm going to go all the way up to the top here so I have the maximum amount of paper here. The Y equation says VIY times t plus 1/2 AY t squared. 0 equals VIY is 0.707 VI times t, which is 138.6 over VI, and then plus 1/2 of negative 9.8 times t squared. That's 138.6 over VI, but that whole thing has to be squared. Now here, the VI and the VI on the bottom, they cancel out. So all we really have is 0.707 times 138.6. And that turns out to be 98. Because that's how we got 138 is by dividing by 707. So if we multiply by 0.707, we're going to get back to 98. Here we have half of negative 9.8, which is negative 4.9. And now we need to figure out what the square of 100, oh my God. So this thing squared on the top is 19,200, that's a comma, 214. Wow. And on the bottom, VI squared. Okay, well, now we got to multiply that number by 4.9. This is getting big. 94,000. Okay, 0 equals 98 minus 94,148 over VI squared. Okay, now we're just doing algebra. This negative term, I'm going to move it to the other side where it becomes a positive term, 94,148 over VI squared equals 98. Now VI squared is on the bottom. You can multiply both sides of the equation by VI squared. That'll cancel it on this side and put it on that side, but on the top. So 94,148 equals 98 VI squared. Now we can just divide by 98, and we get 961 actually, equals VI squared. And taking the square root, we find out that VI equals 30.9, so let's call it 31 meters per second. And that's the most annoying problem on your homework. There's a lot of mistakes that can be made in here, so if you didn't get exactly this answer, but you had all the stuff going into it, you should feel okay about yourself. Actually, if you solve this problem at all, you should feel okay about yourself. All right, number 5's got a little gotcha to it. It asks about some halfway stuff. So number 5, we'll go back to the black pen even though it's misbehaving. Number 5 is a siege engine of some type launched at 450 meters per second. That's really fast. And a 60-degree angle. That's really high. And what we're going to do is we're just going to go ahead and solve this, and then we're going to address the questions that are being asked. So I'm going to solve this completely. That means I'm going to get this pen out here, and we're going to say that VIX equals VI cos theta, which is equal to 450 times the cosine of 60 degrees, which is equal to 225 meters per second. I guess all the pens are misbehaving. VIY is VI times the sine of theta, and that's 450 times the sine of 60 degrees. And that turns out to be 390 meters per second. So now we could fill out our list of knowns and unknowns, and this is for the entire trip, not the halfway. X equals, dunno, y equals 0. VIX equals 225. VIY equals 390. VFX equals 225. VFY equals, I don't know. AX equals 0. And AY equals minus 9.8. T equals, I don't know. What we would do under these circumstances typically is to solve the Y Swiss Army equation, and we would use that to get the time. So let's do it. Divide through by T. Move this to the other side. Now we need 390 divided by 4.9. 79.6. Wow, more than a minute. Okay, then the next thing we would do is we would find the distance. I'm just going to do that right next here. Let's choose a new color. What color? I guess we can use the black. Wow, 17, almost 18 kilometers. 15 miles. I don't know, maybe less than 15 miles. Wow. Okay. What else? Oh, I guess we could find this final velocity. Let's. Oh, whoops. Got to circle this too. Let's move into this blank area and find the final velocity. Final y velocity is going to be initial y velocity plus ay times t. Final y velocity is going to be 390 plus negative 9.8 times 79.6. Final y velocity is going to be, let's see, let's do the 9.8 times 79.6. And so we're going to have 390 minus that last answer. And that's going to be negative 390. Hey, there's your proof. Okay, we haven't even addressed what the question was. The question says if the cannonball comes out with a velocity of 450 meters per second, how high will it get above the ground? So now we're going to address these questions. I'm going to go ahead and do this and just kind of cover it up here and then say we're still working on number 5. But now we're going to address the question of what happens if we let the cannonball just go to its highest point. Okay? And for that, we need a new list of knowns and unknowns. It's very similar to the other list. But now the x position is going to be half of what it was before. So half of 17,908. So let me put in 17,908 divided by 2 equals, that's going to be 8,954. Y is going to be I don't know, because for this situation we don't know where it is in y. VIX is going to be 225 and VIY is going to be 390. That stays the same. VFX is still going to be 225, but VFY is going to be 0. That's right, it momentarily stops in the y direction. The accelerations are the same as before. And the time is half of the other time, half of 79.6. 39.8. So now we can solve for the final, for the y height using just about anything. Don't tell me. Swiss Army. Okay, fine. Actually, let's use a different one. We're constantly using the Swiss Army. Let's use this one. We haven't used this one in a while. So VFY is 0, VIY is 390, that needs to be squared, plus 2 times negative 9.8 times y that we're looking for. Okay, 2 times negative 9.8 is 19.6. So 0 equals, and what's 390 squared? Oh my gosh. 152,100 minus 19.6y. Take this negative term, get it to the other side, 19.6y. And that equals 152,100. And so 152,100 divided by 19.6 equals, and then we get a y of 7,760 meters. So this is the answer to part A. Part B, how far away from the cannon will it reach that maximum? This is the answer to part B. Part C, how long will it take to reach that maximum? This is the answer to part C. And what is the final velocity, magnitude, and direction of the cannonball? You know, we can pull a cheat on that because we've demonstrated that at the end of the process, we have the same two components, just one of them's opposite. So the final velocity, this is what, D? The final velocity is going to be 450 meters per second, and the angle is going to be negative 60 degrees. That's what's going to happen. So there you go. That's problem number 5. I'm sorry, I was below the line here when I wrote these two things down. That's problem number 5. Problem number 6, nice palate cleanser. A little dessert at the end of the activity here. We have a riverboat problem. So we have a riverboat problem. Draw ourselves a river. Draw ourselves a little boaty boat going across the river. And here's the intended landing zone. But there is a current, so our real landing zone is going to be over here at distance x away. And this boat can go 8 meters per second and the current is 2 meters per second, and the river is 64 meters wide. Now, if you do this the old x direction, y direction way, then we should probably solve the y direction first. And the y distance is 64 meters, and the y velocity is 8 meters per second, and so t is going to be 8 seconds. Then we use that in the x direction, x equals vx times t, and x, the unknown, is going to be 2 meters per second of x velocity times 8 seconds, and x is going to be 16 meters. If you do it using the vector way, let's do our two triangles. Triangle number 1 has a 8 meter per second y velocity and a 2 meter per second x velocity, and so the boat will actually have that velocity. These are velocities. And then our triangle for distances will have 64 and an unknown amount, and this vector is our displacement vector. And those are similar triangles, so we can conclude that 2 is to 8 as x is to 64. The sides are in a ratio to each other. Oh yeah, I forgot to write. These are our displacement vectors. So, solving this problem, we have x equals 64 times 2/8. X equals 16. Either way, it works pretty well. All right, folks, that's your homework. I'm signing off.